My name is Dan Blanchard. I'm here from Educational Testing Service, or ETS, and today I'm here to talk to you about a tool we developed for trying to simplify machine learning. But before we get into the tool itself, we're going to have a quick history refresher. So, as some of you may recall, in 1912 there was a boat called the Titanic, and because of an unfortunate event with an iceberg, many of its passengers ended up in the water. The lucky ones ended up in lifeboats. The not-so-lucky ones ended up just in the chilly depths. And because of this, obviously, the ones who were in lifeboats survived. The ones who were not in lifeboats perished. But the thing about this is it wasn't just luck. It wasn't like, oh, yay, I happened to be standing next to a lifeboat, you know, that kind of thing. There are certain properties about people that we can use to predict, based on this data set, whether or not people survived or not. So, for one example, we might say that someone who was in a first-class passenger who is female, had one sibling, whether or not that's relevant, we're not sure, and was 35 years old, survived, but these other two people who were third and second class, different genders, different numbers of siblings, and different ages didn't survive. So the question is, can we try and predict survival from the data? And so this is the data set we're using here is from the Kaggle Titanic Machine Learning from Disaster data set. And so we've got 891 training examples and 418 test examples, in case people are keeping track. So what we're going to use to try and, the tool we developed that we're going to use to approach this problem is, we call it SciKit-Learn Laboratory, or SKLL. Typically we just pronounce it as SKLL for short. Because it's just easier than saying SKLL over and over again. And the idea is, it's where the learning happens, as one of my colleagues coined. So first we're going to look at, well, first we need to actually get the data in a format we're going to use. So in this case, the test set you download from Kaggle doesn't have the labels because it's the test set. So for development, we're just going to split the training set up into training data and dev set, so 80% and 20% split. And on our GitHub page in our examples folder, we have a script that you can use to do that for you called make Titanic example data. And you'll see something print out something like this that says, loads it up, and then it writes out a bunch of different files. So in this case, we've got we split the features that are available in the data set up, so we try to semantically group them. So we've got socioeconomic status, information about their family, their vitals. Miscellaneous is just whatever was left over. And then we have directories for training, development, and then we have one directory that's got both of them combined in case we might want to use all of that later. So the next step, if we're going to try and do this classification task, is pick some classifiers to try. So in this case, we're going to use a decision tree learner, naive Bayes classifier, random forest, and support vector machine. So we sort of get a bunch of different ways to try and approach this problem. So at this point, if you were using scikit-learn, you'd normally have to write some code to load up the data set in a format that you can use, and then get going. But in this case, we're going to instead create a configuration file, which is how you basically do everything with SKLL. So the config files are the simple config parser, Python config parser, ini kind of format. So in the first section, you can see we just have general, where we have the name of the experiment. The task is an evaluation task, which means that we're going to train on one set and test on another set. The input section is where you just sort of talk about your your feature files that your input. So the train directory is a directory with feature files for the training the learner. The test directory is obviously a directory with feature files for evaluating performance. The feature sets list we've got here, it's a list of lists because you could, in one config file, actually try and do different variations. So you might have a list that just had family and miscellaneous, one that had just socioeconomic and vitals. You can sort of do a bunch of different experiments all in one go by listing out different feature sets. So that's why it's a list of lists. So as I said before, we grouped the features up semantically. So family's got number of siblings, spouses, parents, and children. Miscellaneous just had departure port because I didn't feel like that fit anywhere else. Socioeconomics is the fare and the passenger class, and vitals is just the sex and age. Next, we have the list of all the different SciKit-Learn classifiers we're going to use. And here the names are just the names of the classes in Scikit-Learn. So if you're familiar with any of the learners in there, it's pretty easy to just list those all out. Something that, if anyone saw my talk at PyData last year, so far everything's pretty similar to what I talked about last year, but we actually recently released Skull 1.0, and as in recently, I mean yesterday. In that release, we added a bunch of new features, including these ID column and label. Well, ID column is new, label column was there before. But so if you're dealing with CSV files, we used to require you to like change the names of the columns in the CSV file to be like ID is the name of your column that has the instance IDs and stuff like that. Now you can actually just say ID column equals passenger ID, and you're all set. So that won't get treated as a feature, which would be kind of annoying. Then we have the output section, which says where we want to store the results. So the results, we store sort of 3 different types of files. We have, first we have sort of human readable results files that list a bunch of statistics about everything that happened, a confusion matrix, things like that. Then we have JSON files that you can use for automatically processing the results if you want to write a script that does something with them. And then we have a summary that will summarize for a given configuration file, like what the performance was for all of the different learners on all the different feature sets. And that's just in a TSV file so that you can load that up in your analysis tool of choice and maybe, plot the performance and things like that. You can also serialize the models by specifying a models directory, and that'll store all the trained models. So after we have this config file created, all we need to do is run it through this tool we have called Run Experiment. And you'll see something like this where it'll just print out about the loading messages over and over and over again if you're running this on your machine. And you might think, well, why are you wasting time loading the data files many, many times? Well, that's because one of the things with Run Experiment is it was designed sort of from the ground up with the ability to schedule a bunch of jobs on a Derma-compatible cluster. So if you've got like SunGrid Engine or something like that set up where you work, this will use a library we also created called GridMap to actually schedule a bunch of jobs on the cluster for you. So because of that, to try and save memory on the server that's actually submitting all the requests, we don't usually load the files, and then send out the jobs with everything already loaded. The jobs actually individually load the data files so that you can just sort of have pointers that you're passing around. Well, names of file names you're passing around. Anyway, so that's why that might seem strange at first. And okay, that's all I wanted to say about that. So obviously, the next step is we want to see how we did. So this is one of those human readable results files I was talking about. The pretty colors are because it's a presentation and I went in and changed the colors. So sorry, it will just be black and white if you look at it normally. But you can see, we have all sorts of. There's actually more information provided in the file, but I just wanted it to fit on a slide, so I compressed it somewhat. But we have all the basics. You want to know. For reproducibility later, you might want to know like what version of Skull were you using when you ran this experiment, what version of Scikit-Learn did you have installed, how long it took, everything like that. And then we've got this nice confusion matrix at the bottom with precision, recall, and F-measure for each class. In this case, the 0 means that they perished, and the 1 means they survived. So with this basic config file we created, we're getting about 81% accuracy on our little dev set that we created. So getting the results out of the summary file that I was talking about before, we can see that for this task, the random forest classifier seems to do the best, which I think is a common theme sometimes. And decision tree wasn't far behind, neither was SVC, but multinomial naive Bayes did about as well as we might expect that to do. So the next thing we can do is try and tune the learner. So in the previous case, we were just using the default hyperparameters for all the classifiers, which might be okay, but we can probably do better. So, or I guess I answered my own question: can we do better than the default hyperparameters? So to do tuning, you just need to add a small section to your config file, the tuning section that says if you want to do grid search or not, and then what the objective function is that you want to train on. We support a wide array of objective functions, basically all the ones that are in Scikit-Learn, plus a couple more that we found useful in our own work, like quadratic weighted kappa and things like that. And then this shows you what the tuned evaluation results were. So using tuning, somewhat unsurprisingly, helps a little bit. So the random forest classifier gets even better. It didn't help for 2 of the learners, but it helped random forest and SVC get a little bit better. But I should mention that tuning is much better suited to larger data sets, and in this case we're using a very tiny data set for this example. So now that we sort of have a rough idea how things are going to work, let's try and use all of the available data to generate predictions on the test set. Because in the end, if you're doing a Kaggle task, you want to actually have something you submit to Kaggle and have them tell you how well you did. So in this case, we just need to change the task in the general section to predict instead of evaluate like it was before. We've just modified the training directory to be train plus dev, which is the directory where we had both stored in. And in the output section, we say we want to store predictions in a folder we're calling output. I should say that all these directories, I'd say most of the time you're doing this would probably be absolute paths, but it's just for simplicity. I was just using relative paths here. So if we submit all those to Kaggle, unfortunately there's no automated process for doing that, and they limit you to I think it's 10 submissions per day. So to actually get these results on this next table, I had to submit everything manually, drag it all over, and then wait till the next day and do it some more. So this table was hard-earned. So we can see sort of across the board there's a drop in accuracy versus was on the dev set, which I don't think is that surprising because we were tuning on a very small data set, and the test set here is much larger than the set was, the dev set was before. But still in the end, a tuned random forest classifier comes out the best. And so we've done all these different experiments, but we actually didn't have to write any code, which is kind of the reason we developed this tool in the first place, because we have a bunch of people in my group who don't necessarily do a lot of coding, but they hear about different classifiers that are useful for things, and they say, I have this data, and I'm just going to throw it at this classifier and see what happens. And so that's kind of what SKLL facilitates. You can just say, I'm going to try every classifier in Scikit-Learn and see what happens. So just discuss some of the cooler things we have that aren't just config files. So we can read and write ARF, CSV, JSON lines, libsvm, megm. NDJ is just another extension for JSON lines. It's just new line delimited JSON, and TSV data. So one of the nice things about that is that if you want to run the experiments with SKLL and then say check out how Weka can perform on the same data set, you can have an ARF file that can be read by Weka and by SKLL. Or if you want to use libsvm directly or megm directly, any of the files will work with both. So to facilitate the tuning, we have parameter grids that we've sort of pre-specified for all the learners that we support. We've put a bit of work in trying to make those pretty reasonable, so there's not like a million different points in the grid so that it takes 10 years to do your search, but it's also not just like try one setting or another. So if you're curious about what those look like, we have those listed in our documentation, and you can actually override them if there's some better parameter grid that you have in mind for your particular problem. A cool thing that we added yesterday, well, to the release that came out yesterday, is you can now have custom learners, so not just the base learners that come with Scikit-Learn. You can also use anything that's implements a base estimator interface from Scikit-Learn. You can use. You just have to specify a path to the Python module in your config file. I mentioned that we use GridMap to do a lot of parallelization of experiments, because typically we're running huge numbers of experiments on our cluster. The huge number of experiments typically come from our support for ablation experiments. So an ablation experiment, for those who don't know, is an experiment where you try basically all. In the most extreme view, it's all combinations of features, but usually it's just you try all the features but one, or all the features but 2, you can sort of set the number, and then you keep repeating that until you've tried, all of the combinations like that. So if you've got a bunch of features, doing that is going to create a whole ton of jobs on your cluster if you've got a cluster, or just completely swamp your machine if you're running it on one machine. We also added the ability to collapse and rename classes from the config file. So the example I usually give is if for some reason you were working on a task of, say, classifying pictures into, pictures of animals into dogs and cats. Maybe initially when you approached this problem, you labeled the data with like individual breeds of dogs, and then later you decided that that was ridiculous because it made the problem a lot harder. So you just decided to collapse the classes into just dog. You can do that pretty easily by specifying a little mapping in the config file that says, like, beagle and dachshund go to dog. And you don't even need to modify your actual files, which is nice for if you change your mind back later. We have support for all the SciKit-Learn feature scaling stuff, so standard deviation and mean scaling. To try and get your features between -1 and 1, which can be important for certain learners. It's just a matter of specifying scaling equals true in the config file. If you're doing regression, we have rescaled versions of all the regressors so that you can rescale the predictions to be closer to your observed data, which can come in handy in some particular cases. We're also all about command line tools. So we've got tools for joining, filtering, and converting feature files. So if you've got a bunch of feature files that you want to put together or split up, or you've got a CSV file, but you'd like to try using that same file with libsvm in addition to using it with Skull, you can convert it to libsvm. There are actually people out there who only use our tool for converting data file formats, which makes me a little sad, but at least they're using it for something. And then last but not least, we actually have a Python API too, but since we advertise this as you don't have to write any code, that's not our emphasis. But the Python API is pretty simple. There's like a learner object that has basically methods that correspond to all the different tasks that were in the config file. So there's like evaluate, predict, cross-validate, that kind of thing. So here's our lovely list of currently supported learners. So we've got some that are just classifiers, some that are just regressors, and then some that there are both. So this is all of the classifiers and regressors that are in the choosing the right estimator flowchart on the SciKit-Learn documentation. So we don't do any unsupervised learning yet. It's not to say we won't in the future. It's just that's what we needed at first was just supervised. So that's what we covered. I would like to take a moment to acknowledge all the contributors to Skull, other than myself. And so these are all the other contributors, basically all from ETS, except for Niels, who was an intern at ETS, but he's from the University of Pittsburgh. And that's ordered by number of commits in case anyone is keeping track. And so this sort of has, where you can get the data set, where you can get Skull itself. If you want to see the ridiculously long Skull 1.0 release notes, because it took me forever to write them, so, someone please read them. Then we've also got, read the docs documentation, which is much better now than it used to be. We've got a tutorial on there, which is basically a text form of this talk. And we've also got, we've just sort of reorganized the documentation in case anyone saw what it looked like before. It wasn't that great. And as I said before, all the configs and data splitting scripts are in the examples directory on GitHub. And that's mostly what I had to say. So thank you. Sure, go ahead. So that's the best we got on that particular task. I mean, we've used it for other Kaggle competitions and actually, done pretty well. But because there was a Kaggle, well, we've used this as part of models that we've used for Kaggle. There was the automated scoring. There were 2 automated scoring competitions, ASAP 1 and ASAP 2, that were for automatically scoring different types of constructor responses for tests. And since that's like what we work on, we did pretty well in both of those competitions. But we don't really work on modeling Titanic survivor data. so you know, this was just like a little example I put together. Andy? So the question was, how do we distinguish continuous and discrete variables? I guess under the, you mean for prediction, like for labels? Right, so we're using the dict vectorizer under the hood, so anything that's, you know, categorical and string valued gets, you know, the one hot encoded, turned into binary features, right? For integers, we're not really doing anything special for integers. We're just, you know, treating them like numbers. I don't know. If you have a reason to think that that's the wrong thing to do, maybe we can reevaluate that. Mike? So we don't, so I feel like pipelines is, you know, that question comes up a lot. So we don't currently support pipelines because we sort of have, under the hood, we're not using pipelines under the hood, but we are doing basically the same sort of thing. You know, have a sequence of steps that we always perform. So it's like there's always scaling before you do, you know, before you apply, like, you know, the mapping to collapse classes. You know, there's like sort of steps that we take in order that are always in there that are basically a pipeline, but we didn't use a pipeline originally, and I can't remember why at this point, but it's just kind of stuck around like that. Well, so you could do some pre-processing on, yeah. I think usually what we're doing here is for us, we're usually taking data that people have generated. You know, they have some script they wrote for generating these features, and then we're just, you know, performing machine learning stuff on it. So it's usually like the learning and the feature generation are sort of like very separate tasks with Skull usually. But now that we added support for custom learners, I think you could probably pretty easily use a pipeline with it. Now that I think about that, but I haven't tried that yet, so you can let me know if that breaks anything.
In terms of use cases, if someone is already using SciKit-Learn or considering using SciKit-Learn, what kind of guidance would you give as to possible use of Skull?
So the reason I would suggest using Skull over SciKit-Learn, I mean, SciKit-Learn's great. Obviously, we're building on top of SciKit-Learn. But it's just, for me, it's a lot simpler to just put together this little file and, you know, hit go and have it run all the experiments for me. I mean, we've taken a lot of care to try and make sure that we don't make common mistakes about, you know, like when you're doing scaling, making sure everything's correct. And we do a lot of stuff under the hood, so, you know, when it reads everything in, it automatically reads it in as a sparse matrix. But then if you try and use it with a scalar that doesn't support sparse matrices, or with a classifier that doesn't support sparse matrices, it automatically converts it to dense for you rather than just crashing. You know, there's like a lot of stuff that we do to try and make it so it's really hard to screw up. So we try to hold your hand a lot. Print a lot of warning messages when we do stuff like that, but, you know, you'll be fine. And when does this actually end? 10:25. Okay, so I got 5 more minutes if people have more questions. Oh, so the people who don't know Python, so for example, I'm just thinking my primary area of work is I work on a program called eRater, which is our system for automatically grading essays. And so one of the components of that we're trying to add in is a system for trying to tell if essays are coherent. So it's called discourse coherence. So, like, is there a flow to their train of thought as they're writing their essay? So one of the primary people who works on that, she doesn't really do any much programming at all, but she's sort of got a bunch of data that's annotated for coherence, and then she had some engineers like myself, you know, write little scripts to examine different areas of it. So she had all these different features that people had generated, and then she just put it together in a CSV file and passed it to Skull, and then was off and running, and now she has a coherence model that kind of works. Any other questions? Yeah, the slides are already up on SlideShare. I probably should have put that. Well, I guess how would I put a reference to the thing that I didn't upload? You know what I mean? Like, I feel like there's some circularity there. If there aren't any other questions, I do have bonus slides that I was saving. Bonus slides. So this is actually the Python API, in case people care what that looks like. So we've got two main classes we've imported right here, learner and reader. And you used to have to specify which type of reader you were using for all the different files. There's like NDJ reader, MegaM reader, CSV reader, that kind of thing. But then we added this method to the reader parent class for path. So you can say, I just want the reader that works for this file, and this file ends in .megam, so it does a simple lookup and says, okay, that's an extension that maps to this class, which is MegaM reader. And then you just call .read on that to read everything into a train examples, which is an object that we have called feature set, which is basically what we work with are these feature set classes. So if you want to train a linear SVM, you just... Why is that making weird noises behind me? Sorry, that's very distracting. So learner SVC is the name of the SciKit-Learn class. So you just pass in the name of that, and that'll get you a learner that's set up with the default parameters and everything. Oh, I should mention one of the things we do for reproducibility, because a lot of the work we do, we want to make sure that we always get the same results when we run the same model over and over again. So we fix the random seed for like everything across the board has the random seed fix. So if you run this, 10 years from now, it should still give you the exact same output, which is very important for our work in particular. You can override that, I guess, if you wanted. So you just call .train with your example set, and that'll train your model. Now that you have your trained model, you can load some test examples, and you can call learner.evaluate on it. And so learner.evaluate returns a tuple of a ton of stuff, which is kind of like, as we were going along, we needed more and more things that it needed to return, and so they kept adding on. So we've got the confusion matrix that shows them the output file, the overall accuracy, the precision recall and F-score for each class, the tuned model parameters, and the objective function score on the test set. And generating predictions is really easy. It'll give you predictions as a, I think it's just a NumPy array. And then if you want to do tenfold cross-validation, you just call it cross-validate. And this fold result list here is basically a per fold version of the results from evaluate. And then in addition to that, we return the per fold training set objective scores, where the training set is the training set within the cross-validation. And what's this? Wait, that didn't come up yet. Okay. And then the other thing is, you might want to write some files. That's actually a really nice feature is, for writing out feature files that are in different formats. So this sort of shows you how you can create a feature set by just basically getting a list of labels, a list of IDs, a list of features where features are just dictionaries that map from feature names to values. And you can create a little feature set, and then you can just get the corresponding writer that can write that type of file using the for path thing, or you can just directly say like ndj writer dot whatever. That should not have a dot there. So it should just say ndj writer, and then it's the initializer, so it shouldn't have a period there. I apologize for the typo. Then you just write it out, and you have a nice new line delimited JSON file. So that's the basics of what's going on under the hood a little bit. And now my time is actually up, so thank you.